Hi everybody. In the last video we used a model containing polynomials of time to fit to the data, and we saw that adding polynomial trends to our model made us explain the data quite well. However, in data explanation or in data fit does not equal out of data fit. So in sample fit does not equal out of sample fit. Okay, so we are now going to talk about something a bit more robust, which is autoregressions. So what is autoregressions? An autoregression is a regression that uses prior values of the response as a predictor. Okay, so for example, your response is y at time t. This is what you are going to explain or predict, and as predictors you use the lags or prior values. So for example, time t minus 1 or y equals time at time t minus 2. Okay, so for example, you use the price of houses last month to predict the price of houses this month. Okay, so the simplest autoregression is a one-lagged autoregression. We call that first order autoregression, or AR1. So this is, for example, price at time t equals an intercept plus a coefficient or a slope, and price at time t minus 1. For example, yesterday or previous hour or last year. So and you can also add more lags. So for example, you can have a third order autoregression, AR3 autoregression lag 3, which contains all of the lags at time t minus 1, t minus 2, and t minus 3. Okay, so let's go to our case study. We have the unemployment rate, and we in the previous video we used the polynomial trend to explain the unemployment rate, but we saw that we couldn't really trust the forecast. Okay, so what are we doing now? We can create more lags. For example, unemployment rate t minus 1. So what do we fill this with? Okay, so we want to create one lag. So we have month 2009, month 1, which is January, and the unemployment rate was 2.26, but we really don't know the unemployment rate at time t minus 1, because that would be year 2008, month 12. We don't have that in our data, so we just get nothing. Okay, but the lagged value for the second entry here is for 2009, month 2, and the value for t minus 1, which is the previous month, we have that here. It's month 1. Okay, so this goes down here and gives us 2.2666534. So this is the value of y, our unemployment rate, last month. And we do the same for this third entry. So that's for month 3, and the lagged value is then for month 2. So we get 2.460776. Okay, and we just continue. Okay, but we can also make other lags. For example, third lag. Okay. Then we have the unemployment rate for lag 3, and for the first one we get nothing, and for the second one we get nothing, and for the third one we get nothing, because we are trying to lag three months back, right? But if we get down here for month 4, we lag 1, 2, 3, and then we can see that we use the month 1 unemployment rate. Okay, so for the fourth entry here, we use the first month unemployment rate, because that's time minus 3. So that would be 2.266534, and for the fifth month we use t minus 3, which is 2. 5 months minus 2 is 2.460776. Okay, so now you get the idea behind it. Okay, and what we do is that we declare the data set as time series instead of, to take advantage of the lagged operator L. And what we do is that we just say, instead of, we say time series set month, because we have the month variable here, which is a time, our time variable. And if we do that, then we can relate to these two lagged variables with the following commands. They are now called L1 dot unamp rate. Okay, so which means that this is just unamp rate variable lagged once. Okay, and this is down here, and this would then be L3 dot unamp. Let's see if we can write that properly. Okay, which means that now that you have declared your data set as a time series, it's quite easy to include lagged variables in your regression. Sorry about that. So for example, if you would make an AR1 or fit an AR1 model to your data, you would just write regress unamp rate on L1 unamp rate. And now you have the autoregressive model, and you get some coefficients. Okay, some results. Super easy. Okay, and you can do the same with an AR3 model. You can just write regress unamp rate on L1 unamp rate. Okay, I'm getting quite low on my writing pad here, and you would have the L2, and you would have the L3, unemployment rate. Okay, and if you declare the data set as time series, then you don't need to add these variables manually to the data. Stata does that for you. Okay, in the regression. So, for example, we run the AR1 model, and here something special is going on, because we are saying that as long as you go 3 sorry, you are not counting the or including the 3 first data points, the 3 first rows in your data set, because we are going to fit an AR3 model later. And you see that if you lag something 3 times or by 3 periods, then based on your data, you can't have any values for the 3 first entries of your data, because you don't have that information. Okay, so which means that these are not included in the regression. So you only include the entries for which you have full data. And just to be able to compare the AR1 model, the model with 1 lag, and the AR3 model, the model with 3 lags, then we are cutting off the data we are looking at and starting at data point 4, okay, row number 4, and downwards. So you remember from the polynomial example that we had 129 data points, and which means that the 3 first data points, we had 129 minus 3 equals 126. So now we are only using 126 data points to estimate the regression. Okay, so what do we get? We get the p-value for the f-test says that our model, it's explaining a significant part of the variation in our y variable in unemployment rate, and the adjusted r squared. The adjusted r squared is 0.944, which is basically as high as the model with several polynomial variables included. So we can explain more of the variation in unemployment just by including one variable compared to generating several variables. So our coefficient here on unemployment rate lagged is 0.98, which means that if your unemployment rate was 10% last period, then you would expect the unemployment rate to fall a bit to 9.8%. Okay, so it's like a mean reverting process. Okay. And if we look at the AR3 model, we just regress unemployment rate and with the 3 lags, and we still have the cutoff here, so we can compare the 2 models with the same data. and we see that it's still relevant, but we have the adjusted R squared is still quite high, but it's not increasing by a great margin. So we have the F test, it's passed, and then we can look at the p-values for the t-test, which means which indicates that all of these lags, they are indeed significantly different from 0. Okay, but you saw that we had some if we were to look at the coefficients, okay, then we can go here and say that the slopes, they are not readily interpretable because they do not include any fundamental variables. Okay, what is actually causing a change in the unemployment rate? You don't know from this model. In the polynomial example, we just used time as an explanatory variable, which did not really work out. But now we're just using the value of the unemployment itself, and we can't really say anything about what is actually affecting the unemployment rate from this model. What we can it's not for analyzing how explanatory variables impact y, because we're only using y itself. What was I going to say? And if we look at now we can go back, because if we look at the first model, the AR1 model, then you see that the only thing we can say is that if you want to predict the next value of y, you can use the previous value times a certain coefficient, and that would be your estimate. Okay, but you can't really say anything else than that. Okay, so you can say that, well, this, if you just go one step ahead, one step further, then you would have this downward sloping forecast, because this coefficient on the first lag is less than 1. If it had been more than 1, then the process would have just increased and exploded into the future. But with 3 lags, then it's becoming more difficult to understand what is the rationale behind the coefficients, right? Because the coefficient on the first lag, it's 0.89 or 0.90, and the second lag, it's positive 0.26, and for the third lag, it's turning negative. Okay, so negative 0.18. So you can't really give a reason why it should be so. Okay, so this is the downside behind the AR model, but as you will see, actually giving quite robust forecasts most of the time. So the problem is, one of the problems with this model is how many lags to include. Okay, and then you have to just start with one lag, and you see what kind of fit you get, and you try with another lag. You just check if the fit, the R squared adjusted, the adjusted R squared increases, and you can see on the residuals, you can check the residuals if the model actually explains any dependence in the residuals. If there is dependence in the residuals, then you can include additional lags. Okay, so yeah, so you just try different lags and look for an increase in adjusted R squared and a reduced standard error, and of course statistically significant coefficients, and also check if the model explains dependence in residuals. Okay, so for example, in our example, we have the AR3 model. It has almost the same R squared adjusted as AR1. So just for simplicity, we pick the AR1 model. And this is if the AR1 model does not have dependent residuals. Always check the residuals after you run a regression. Okay, so this autoregression regression, it lets us capture dependence in the data. For example, in the electricity markets, you have these 1 day cycles and 1 week cycles, where you have lower prices in the weekend and higher prices during the weekdays. And with a lag, just by including a lag of 7 days, you can actually capture that weekly seasonality. Okay, and if you have quarterly data, then you could include 4 lags and capture the yearly seasonality. Okay, so for example, always check the residuals, and we have the residuals from the 5th order polynomial regression from last video, and you see here that you have this you can actually see that these residuals, they are dependent, because if the residual goes upwards, then most likely the next residuals is even higher, and if it goes downwards, then the next residuals is probably lower. So we can fit the or plot the residuals here on the lagged residuals. This is for time t. This is residuals for time t minus 1, and we have the correlation here. It's 0.72, which is quite high, so they are indeed positively correlated, and which means that residuals of or in the fifth order polynomial regression are dependent. Okay, so and we can check this by the Durbin-Watson statistic, and the Durbin-Watson statistic gives us 0.5496, and remember that the null hypothesis is for the correlation between the true error at time t and the true error at time t minus 1. It should be 0, which means that the alternative hypothesis is for this correlation of the true values is different from 0. Okay, and we can get the Durbin-Watson stat equals 0.54, let's say 5496, and this is actually smaller than the critical value of 1.69, which is the critical the lower critical value, and if the Durbin-Watson statistic is lower than the lower critical value in the Durbin-Watson table, then we can say that we can reject H0 of no correlation in the residuals, which means that we have autocorrelation. Okay, and this is actually a violation of the multiple regression model assumptions, which means that we can't really trust this polynomial regression model. And what we can do is to check the residuals of the autoregressive model, and just by using one variable, we can actually explain more of the variation in the unemployment rate given by the adjusted R squared, which is higher. But we also see that when we check the residuals, we can get basically no pattern. Okay, you remember that in this plot of residuals against residuals at time t minus 1, we could actually fit this positive slope line with the residuals from the polynomial regression, and whereas with the residuals versus the lagged residuals from the AR1 model, the autoregressive model with only one lag, we can't really fit a line with a positive or negative slope. Okay, we are not we are not using the Durbin-Watson test for AR models, the autoregressive models. We'll come back to that. Okay, case study. Forecasting unemployment with AR1 model. What is the forecast for October 2019? That is one period beyond the data. So we have the unemployment rate at time t, which we are trying to explain, and we have the one lag model, and then we have the intercept of 0.409929. We have the intercept 0.049, and let's see, no, that was 0. I remember it was something 9929 plus the slope, which was very close to 1. No, that was not it. Let's see. 386. Okay. Times the lagged unemployment rate. Okay, so this is our fitted equation, and how can we use it? So we want to forecast unemployment rate for 2019 month 10, right? Which is equal to the intercept plus the slope times the unemployment rate for period 2019 month 9. Okay, so we need the unemployment rate for September. So we need the unemployment rate for September, okay? Which means that we can just plug that in, because that's 2 point, let's write that here, September in 2019, which equals 2.2642, which means that we can use our model, plug in the unemployment rate for last month, and get the unemployment rate for 2019 month 10 equals 2.2687, which is quite close to last month's unemployment rate, but it's a bit higher. So we are forecasting a slight increase in unemployment rate. And by using the standard error from the regression, then we can use that to make the 95% prediction interval. So the prediction interval is this unemployment rate, 2.2687 2687 plus minus 2 times the standard deviation of the residuals. And the standard deviation of the residuals, you can find that here. It's SE, the root MSE, root mean squared error of the residuals. It's 0.05511, which means that this is equal to 2.2687 plus minus 2 times 0.05511, which gives us an interval of 2.15678 to 2.3806. So we are 95% confident that the true value in 1 month will lie somewhere in this interval, 2.15 to 2.38. Okay, so what is the forecast for the next model or next period, the November 2019, which is month 2019 11. Okay, so what we do is that we just plug in for this estimate. We use the same model, the same coefficients for 0.9929 plus 0.98380605 times the unemployment rate for 2019 month 10, which we just calculated in the last slide, which is 2.2687. That was our estimate. So this is our estimate, and this shows that we have to use our previous estimate to make the new estimate, because we don't have data for month 10, the October. We have no actual data for the October 2019 unemployment rate. Okay, and this shows that you can just reiterate your model and create a forecast for as long into the future as you want. But continuing with this example, we have to just plug in 2.2687 for the unemployment rate for last month, and this will give us a unemployment rate estimate for November, which is 2.2731, which means that our model it's forecasting or giving us a forecast which is slightly upward sloping for the 2 next months. And something really important is the prediction interval, because the first prediction interval is quite easy to calculate. We just use the standard error of the, or standard deviation of the residuals from the model. But when we use a forecast as a dependent variable, then we introduce extra uncertainty into the model, okay? Because what we base our November forecast on is the forecast itself with its uncertainty. It's not a true value, okay, or absurd value. So when forecasts are used in place of observations as X variable, then the uncertainty is compounding. So for example, you have this process, this Y, and this time, and you have these true values, okay? These are true values. And you have the forecast. Then you can make these forecasts, okay, for as long into the future that is practical for you, or not necessary. But what you will find is that the uncertainty band is actually increasing. This is, for example, the 95% prediction interval. Okay, so the prediction interval, it's just widening if you are looking further and further into the future. Okay, so what you need to do after you have estimated the model is that you check the model. So, or before you estimate the model as well. So you have to check the multiple regression conditions, that the relationship between the Y variable for example, if you want to use the lagged Y variable, then you can plot these against each other and check if the relationship between these are linear. And you can check if there are any lurking variables by using your knowledge about the market and just thinking about what might affect Y. And after you have estimated the model, you have to check if the errors are independent, and which you can do with the Durbin-Watson statistic if your time series is not including any lags of Y, but if the model includes any lags of Y, then you should not use the Durbin-Watson statistic. And you just check, this would be the correlation of the error with its own lag. And you have to check that the errors have similar variances, for example, across time. And that the errors are nearly normal. Then you just use the histogram. Okay, so And the most important of these in time series context is the independence of the errors, because it's quite often that the residuals the residuals are correlated with its own lagged value. So if if they are not independent, then you can't really trust the standard error and the standard errors of the slope, okay, which gives you the impression that you have a better model than you actually have. So, and you can use the Durbin-Watson statistic to check dependence if you have no lags of y. Yeah. Okay. So here you can see some dependent versus independent residuals, which means that they are from a time series regression. Okay. So, for example, these are independent, whereas these are dependent. Because here you see that if you have, well, you get kind of trends in your residual plot, and if you do that, then you should check the correlation of the errors on its own lags, or the Durbin-Watson test if you have no lags of y. So the summary and best practices, it's just to examine the plots of residuals when you fit time series. Okay, so for example, you want to plot the residuals, and a nice way to do that is to use the two-way connected and E, that's the residuals on the y-axis, and time on the x-axis. And then you should make this scatter plot of residuals versus fitted values. Then you actually make this is the y hat. So you first make the y hat variable by predict y hat or predict y, and then you can use the two-way. Let's see if we can write that. Scatter of residuals versus y hat. Okay, and then you should make the scatter plot of residuals versus lags of the residuals. So then you would just this is ET, and lags of the residuals is ET minus 1. So then you would just, because then you can see if there is any linearity. If there is any linearity, then you could use the residuals for the previous period to say something about the residual the residuals of the next period, which should not be possible. Of E on L1 dot E. So if you have defined your data set as a time series, then you can use this L1.E command to make like a lagged variable. So by checking these three time series or scatter plots, then you can look for dependence in the residuals. And by using autoregressions, you can help dealing with this dependence, because if you find dependence, then you try to add one extra lag, okay? And if you still find dependence, try adding one extra lag, okay? And of course, avoid polynomials with high powers, because they can be quite deceiving, giving you a very high R², but they are not working very well when it comes to forecasting. It's much better to use the autoregressive model. Okay, so that's it.